Hello, right, this video we're going to look at using differentiation to solve an optimization problem or model with differentiation. I've copied most of this from the PowerPoint, but I just quickly go through the kind of pattern that the exam questions tend to follow. So you'll usually have two variables, and often one of them you have to kind of introduce yourself. Usually about lengths, because we're usually talking about like volume or surface area or something like that. And then there'll be expressions for two different quantities. So one is a constraint where it has to be equal to something. They'll tell you like the surface area is 20 centimeters. And then the other is something that you're wanting to maximize or minimize depending on the question. So you'll try, so given that the surface area is 20 centimeters, what is the maximum volume that the shape can take or whatever? We use the constraint to eliminate one of the variables in the other equation so that it's just in terms of one, which means we can then differentiate, find the turning point, which will allow us to find a maximum or a minimum. Sometimes you will then be asked to prove that the value you found is the maximum or the minimum. I'm trying to talk too fast. The maximum or the minimum. So you would need to use the second derivative to show that you found a maximum or a minimum. So let's have a look at a couple of examples. The first one is this with a tank. So a large tank is in the shape of a cuboid and it's going to be made from 54 meters squared of metal. The tank has a horizontal base and no top. That's important. The height of the tank is X meters and two of the opposite vertical faces are squares. Show that the volume V meters cubed of the tank is given by V equals 18x minus 2/3 x cubed. So a nice show that question to start off with, so that even if you can't show it, you can still use that expression to maximize or minimize the volume. So if I make a quick sketch of what the tank looks like, you've got a cuboid. I'm not sure what I'm doing here. I just didn't think this through. So here is, I should have done this in advance. Here's, all right, and it doesn't have a top. That's better. I mean, that's not better. It's very messy, but it's fine. We're told the height is X, and we know that two of the opposite vertical faces are squares. Just based on my diagram, I'm going to say that it's the left and the right hand side. So if it's a square and the height is X, then that means this kind of depth of the cuboid is also X. The only thing we don't know is the base is here. So we're going to call that Y. And then we're going to use that and the fact that we know the surface area and that we can find the volume of a cuboid to show that the volume is 18x. So as it stands, the volume would be, I haven't really left myself enough room. Can I make this a bit smaller? Just move it out of the way. Can I put it over there? Over here, maybe this is the best place for it. Right, let's put it there. What we've got so far, we know that the volume is equal to x times y, x times x times y, so x squared y. So currently that's our formula for the volume. The surface area is all of those 5 surfaces, because remember there's no top. So all of those 5 surfaces added up together, the area of all those 5 surfaces added up. So you've got the 2 squares either side, which would both have an area of x squared. You've got 2 lots of them. You've got 2 lots of all of the sides, because you've got left. No, you haven't. That's wrong. Hang on. Just write it out. So you've got 2 lots of x squared. So you've got 2x squared. You've got the front and the back, which would both be xy, because the height is x and the base is y. And in fact, the base would be xy as well. So we've got 3xy. So that is our expression for the surface area, and we know that that is equal to 54. Now, just like it says in that black box at the top, we want to use this constraint, which is the surface area, because that has a fixed value of 54. We want to use that to get rid of one of the variables in the volume formula, the volume equation. So obviously, based on the fact that we're showing that it only has an x in it, we're going to rearrange the surface area equation to, it is an equation, yeah, so that it's y equals something. And then we're going to substitute that into the formula for the volume and then rearrange until it looks like the thing we want it to look like. So if I subtract the 2x squared over to the other side and then divide by 3x, I would get y is equal to 54 minus 2x squared divided by 3x. And I'm going to substitute that into the volume, I'm really trying to say this too fast and I'm just tripping over everything that I'm saying. I'm going to substitute the y equals into the formula for the volume. So I get volume is equal to x squared multiplied by 54 minus 2x squared over 3x. Yeah, I'm gonna cancel straight away. So one of the x from the x squared is going to cancel with that x on the bottom. And then when I expand the bracket, I get 54x over 3 minus 2x cubed over 3. And now it's starting to look like the formula for the volume they've given us. Obviously, I've separated that out into two fractions. Whether you do that in this step or the next step is up to you. But basically, the 54 divides by 3 to make 18x, and then that's the 2/3 x cubed. And it looks like the formula that we've been given. So we've shown it. We've shown that volume is equal to 18x minus 2/3 x cubed. That's a cubed. Okay. This part B then, given that x can vary, use differentiation to find the maximum or minimum value of v. So to do that, we need to differentiate the v formula, the volume formula, and then find the value of x when it's equal to 0, because that would be the turning point if it was a graph, or the maximum or the minimum. And then substitute that value of x back into the formula for v to find the maximum or minimum value of y. So, part B, we are finding dv by dx, because we are differentiating v with respect to x, because our formula is v equals and it's in the variable x. So we're finding dv by dx, which would be 18 minus 2x squared. If we multiply the 3 by 2/3, we're left with just 2x squared. We need to put that equal to 0 to find the turning point, and then we get 18 is equal to 2x squared, divide by 2, and then square root. Gives me 9 is x squared, so x is equal to 3. I mean, technically plus or minus 3, but x is a length, so it can't be minus 3. So that's my value of x, and then I put that back into the formula for the volume to get either the maximum or the minimum value of v. So I've got 18 lots of 3 minus 2/3 x cubed, so 3 cubed. I don't have a calculator. I've got my phone. Just bear with me. So 18 times 3 is 54. I knew that. 3 cubed is 27. And then 2/3 of 27 is 18. So 54 minus 18 is 36. And that is the volume, so meters cubed. That is either a maximum or a minimum volume. Without doing the second derivative, I don't know whether it's a maximum or a minimum value. But if the question asks, then that's what you would do. You would then just take the second derivative of the volume formula, and if it's less than 0, it's a maximum. If it's greater than 0, it's a minimum. Yeah, but that's it. The most difficult part is probably the first part, part A, is the show that part, and knowing where to introduce your own variable. Obviously, we had to introduce y. That's possibly the most difficult part of it, but once you've done that, differentiating it's easy peasy, and putting it equal to 0 to find the turning point. You should be able to do that in your sleep. Let's have a look at this. This was the test your understanding question in the PowerPoint. So if you want to pause and have a go yourself, now's your opportunity. I'm going to go through it. So we've got a cuboid with has a rectangular cross section where the length is equal to twice its width. So we've got a length of 2x and a width of x. The volume of the cuboid is 81 cubic centimeters. Show that the total length of all the 12 edges of the cuboid is given by L equals 12x plus 162 over x squared. So our constraint this time is given in the volume, because we know the volume has to be 81. Again, we only know 2 of the dimensions of a 3-dimensional shape, so we're going to need to add in the kind of depth of the shape ourselves. So I'm going to call it y. So I'm going to say this is y. So the volume of the cuboid would be given by doing 2x times x times y, and we know that has to be equal to 81. So that's 2x squared y is equal to 81. But obviously the problem is that we've got an x and a y, and we only want to have Yeah, no, that's fine. The length is equal to all of the lengths added up. So we've got 4 of the 2 x's around the middle. We've got 4 x's around, like, going vertically, and we've got 4 y's going diagonally. So we have 4 lots of 2x plus y, which is 8x plus 4x is 12x plus 4y. We don't want it to have a y in, so we are going to rearrange the volume formula and substitute it into the length, and hopefully we should get something that looks like the formula we've been given. So, taking this and rearranging, we get y is equal to 81 over 2x squared. And then I'm going to substitute that into the formula for the length. So I now have L is equal to 12x plus 4 lots of 81 over x squared, 2x squared. That 4 will cancel with the 2 on the bottom, leaving me with 2 there. So it simplifies to give me 12x plus 162 over x squared, which is what we were asked to show, 12x plus 162 over x squared. So that is our formula for the length. We want to use that and use differentiation to find the minimum value of L. So we're going to differentiate to find the minimum value and put it equal to 0. So we are finding dl by dx, differentiating L with respect to x, which gives us 12. If 162 is, put it as a power of x, it's 162x to the power of negative 2. So when I multiply the negative 2 by 162, I get negative 300. Oh my goodness. My brain's not working properly today. I should be able to double 162 in my head, but I can't. 324 x to the power of -3. Okay, I need to put that equal to 0 and solve it to find the turning point. So I have 12 minus 324 over x cubed. Once I'm solving an equation, I generally prefer to have it back as a fraction. I don't like to have negative powers because that makes it more difficult to solve. I'm going to add the 324 over x cubed to the other side, and then I'm going to cross multiply so I get x cubed is equal to 324 over 12, and then I'm going to cube root that, which is not easy to do on the calculator that I'm using. Oh no. Oh, this is so annoying. Why did I start doing this when I didn't have my calculator ready? You're going to have to bear with me a second. Okay. Oh no. The cube root of... I feel like I didn't get it. Over 12 is 3. 324 divides by 12 to make 27, does it? Yes, it does. Okay, the cube root, so anyways, it gives me x equals 3. Goodness. That was way more difficult. I made that way more difficult than it is. 324 divided by 12 is 27. The cube root of 27 is 3. So x is equal to 3, which means the minimum value of L is found when x is equal to 3. So we're doing 12 times 3 plus 162 over x squared is 9. So that's 36 plus 162 over 9, which is 54. So the minimum value that the length can take is 54 centimeters, I guess. Yeah, centimeters. The last part is asking us to show that this is actually a minimum, so that's when we need to take the second derivative. So differentiating 12 minus 324 x to the power of -3 again leaves us with 324 times 3 is 972. So the second derivative is 972 x to the power of -4. I need to substitute in my value of x that I found to work out if it is positive or negative. So, 972 times 3 to the power of -4 is 172 times 3 to the power of -4 is 12, which is a positive value, which means that we have indeed found a minimum. Obviously you would write that as a little sentence, but I have run out of space, so I'm not going to. But that's your reason, is that when you take the second derivative, substitute x in, you get a value that is greater than 0, that is positive, which means that we have found a minimum. If it was negative, then it would be a maximum, but it's not, it's positive, so it's a minimum. Okay, I hope that made sense. I feel like it's been full of chaotic energy, but hopefully you'll be able to make some sense of it. Like I said, the most difficult part is always the part A, is kind of setting up the equations and the formulas that you need. Differentiating, it's easy. Putting it equal to 0 and solving it, easy. It's the kind of setting up this type of question that's the most difficult, but I think we can do it. It's nice and straightforward. Yeah, hope it made sense. Hope it helps. Have a lovely day.